My name is James Kenley. I'm the Executive Director of the Vail Symposium. And on behalf of our board, our staff, our awesome volunteers, welcome to our in-person audience that braved the elements. We have our first proper snowstorm. It's still our summer season, but winter came early. And to our online audience, welcome to our live streamers, to Melting Ice Shelves, New Discoveries and Immediate Impacts, featuring Dr. Kristen Poinar, Dr. Ted Scambos, and Scott King. In this program, we'll venture to the most extreme climates on Earth, including Antarctica, and we'll connect the dots back to our own experiences in a changing climate. Our dot connector tonight is Scott King. Scott is a tech entrepreneur who has been on Deloitte's Technology Fast 500 and the Inc. 5000 and is in the Ernst & Young Entrepreneur Hall of Fame. Fortunately for all of us, he has turned his focus to the climate through two initiatives, the Climate Action Fund at his alma mater, CU Boulder, and Mission Zero, a nonprofit empowering the next generation to tackle our climate crisis. Our format tonight is a little different than usual. Scott will set the stage. He'll then introduce Dr. Kristen Poinar to share her research. He'll then introduce Dr. Ted Scambos to share his research. The three of them will then be in conversation, and I assure you we'll have time for your questions at the end. Ladies and gentlemen, here and online, please welcome for the first time to the Vail Symposium, Scott King.
I'm glad we managed to make it here tonight. Ted and I weren't sure. We were on the top of Vail Pass wondering if we were going to get down the hill, but we did. So I'm Scott King. I have lived a very busy life in tech entrepreneur and raising kids. And so I wanted to tell you a little bit about myself and why I'm here. First off, so I'm an electrical engineer graduate out of the University of Colorado Boulder. I co-founded with my brother ReadyTalk, which was a very successful tech startup in the communications segment. And Dan and I sold that in 2017, so about 6 years ago. And so I went from a life of frenetic pace to a life of retirement in the matter of a day. And so that I don't know if you've gone through that in a retirement setting, but that didn't settle with me. So I kind of put myself into a place of what do I do next? What's that next chapter for me? And it's one of those things where when you run so hard, so fast, and you don't pay attention to what's going on around you, and then you realize the issues that the planet is facing and the people and the animals and the living organisms on this planet are facing with climate change, it makes you think, okay, this is my calling. And so I've been spending the last couple of years trying to learn about it individually and then trying to engage and figure out how I can make a meaningful difference. And so the two things that I've done is I started a organization called Mission Zero, and it's two parts to that. One part is my own mission to become carbon zero. How do I live a carbon zero lifestyle that's a sustainable lifestyle? The second part is working with the University of Colorado, working with students on climate action, engaging students, supporting students in the work that we need to do on climate change. The other part of that is the CU Climate Action Fund. Try that. There we go. And this is a part of the foundation of CU that supports educating students and faculty and encouraging faculty to incorporate climate change into their existing curriculum that they teach students. So we're not going to have students that only understand climate change because they took environmental studies. We're going to have students that understand climate change no matter what they study. And we're in a crisis, an educational crisis, because we don't understand the issues that are supporting and causing climate change. And I'll go through a couple slides because what I want to do is tee up where we're at in the climate crisis and how it's impacting our ice sheets and our glaciers on both poles, and understand what are the implications of that. And that's the dialogue we're going to have today. All right, I'm going to figure this out before we get done. So this presentation I'm going to start with actually is pulled from the presentation I give students. So I lecture on entrepreneurship, and I also lecture on energy and climate. And this one, I mean, it's hard not to read this and feel like, as a parent and grandparent, we've let our kids down. We're leaving them a crisis, and we haven't armed them to deal with it. And we are the first generation to feel the effects of climate change. And it's happening so fast, we're the last generation that can do anything about it. And that sets the tone for what we're talking about tonight. This is Greece. Greece had a year of rainfall in one day, and in 4 days they had almost a meter of rain in Greece. This is the valley where they grow most of their food. And they're talking about over 10 years before they'll be able to actually get back to where they were before. This is Libya. They lost 11,000 people. I forget how many are still unaccounted. They had so much rain, it broke 2 different dams and just flooded entire parts of their city. Canada had some of the worst wildfires we've ever seen in northern Canada. So much so that New York could hardly see with so much smoke that was coming down. So what's going on? This is the sea surface temperature, and you can look back all the way to the 70s and not see the spike we're seeing right now. This is air temperature, and you can also see this year's spike in air temperature is off the charts. This is the northern summers. This is the top 30 warmest summers that we've seen in the northern hemisphere. And you can see 2023 is breaking the records across the board. 2023 for the Antarctic sea ice has hit an unfortunate number where the maximum ice is the lowest it's ever been. So much so, it's causing a lot of scientists to be gobsmacked. I don't know a different word to use. We're just wondering, are we in a tipping point? Are we in a place where this climate is in a runaway state? And so we're feeling it every day. My daughter and her husband lost their house in the Marshall Fire, which was a climate-induced fire. Our house, we have a house in Winter Park. The insurance on it has gone up 4 times. 4x since we've had it, and we've only had it for about 4 years. It's impacting everybody. The insurance market in Florida is collapsing. It's hard to get insurance in a lot of places, and this isn't getting any better. So how do we understand and deal with this issue? So this is a chart I show students, and this is climate. It's the carbon dioxide concentration, and it's measured in parts per million in the atmosphere. And what you can see for the last 800,000 years is it ranged between 200 and 300 parts per million. And that's the operating range that we have grown up in. All the living creatures on Earth have grown up in this. And what happened here? What happened to that spike? Any ideas? That's the Industrial Revolution. That's the time we started to burn coal, natural gas, and oil for energy. This is what, since 1960, I was born in 62. Our carbon in 62, when I was born, was about 320 parts per million. Today, it's over 420. So in my lifetime, we've doubled the amount of carbon in our atmosphere. And where does that come from? 70% of our carbon is because we're burning fossil fuel. So we're emitting about 50 gigatons of carbon every year, and about 40 of that is from burning fossil fuel. We have to stop it. We have to transition from burning fossil fuel to clean energy for transportation, for heating, for cooking, for industry across the board. That's the job in front of us. We're going to talk tonight about what are the implications of continuing to burn fossil fuel, and what does that mean to the ice, the glaciers, and the amount of water and fresh water that is getting dumped into our oceans. What does that mean to sea level rise? What does that mean to populations on the coast or island communities? So with that introduction, which I know is a little bit depressing, I'm gonna leave you on a positive note, though. We have the solutions in front of us. We have electric cars, we have heat pumps, we have induction stoves, we have the cheapest renewable energy with wind and solar. We can use the car's battery to support the deployment of renewable energies that are intermittent. We understand what we need to do. We need to build a transmission system, an energy transmission system that's a energy superhighway across the United States. And this level of effort is a wartime footing. We have to think about it in those kind of terms. Okay, I'm going to introduce Kristen Point. Excuse me. Come on. Here we go. All right. Kristen Poinar. She is an expert in climate change, ice sheets, sea level rise, and she recently returned from the research from Greenland ice sheets. As a researcher, she uses computer modeling to understand how the Earth's ice sheets are shrinking and contributing to the rising oceans. She investigates how ice and water move and interact with glaciers and how these processes affect the glacier's health and flow, speed, and the rate of the glacier's decline. Kristen's work focuses primarily on Greenland ice sheet. One of her studies found that the meltwater inside certain deep fissures called crevasses can reach bedrock and find its way into the ocean, contributing to sea level rise. And she gave a TED Talk on this in 2017. In addition to the Greenland ice sheets, Kristen's areas of academic interest include the Antarctic ice sheet and the prehistoric, let's see if I get this right, Laurentide ice sheet. All right. With that, I'd like to introduce Kristen.
Thank you. Thanks so much for that great introduction, Scott, and your summary of the horrors of climate change. I'm really honored to be here. It's my first time in Vail. You've got a really wonderful place here and a really wonderful symposium that I'm just honored to be a part of. And I'm really happy to be here for your first snow of the year, too. I think it's really fitting that we're having a polar science night on this day. So in honor of that, I want to take you to Helheim Glacier. It's southeast Greenland's largest glacier. It's a huge ocean-terminating glacier that has gigatons of ice lying in wait to contribute to sea level as the climate warms. And maybe you've noticed on this composite of satellite images, every week or so, going back to 2015, maybe you've noticed some features of Helheim Glacier already. The weather. The conditions are so variable here. Cloudy, rainy, sunny, clear, dry, melty. It all happens and it's changing every week. Maybe you've noticed little areas of blue meltwater here and there throughout the glacier. These come and go during the melt season. They come up, they disappear. They go away, they come back again. It's a really dynamic environment. And maybe you've also noticed that the ice is moving. And these are images that we take from space. We can see the ice moving from orbit. It's moving that fast. The ice moves from west to east. So the interior of the mighty Greenland ice sheet over here, and it's got a steady flow to the east into the fjord, which is filled with bright white icebergs. These bright white icebergs have cracked off the front of the glacier and flipped over, so they're showing you the pristine inside of the glacier, ice that hasn't seen the atmosphere for thousands or tens of thousands of years. And they fill the fjord, and then the flow of ice to the east pushes them out to the open ocean. And maybe you've seen flickers of dark blue water here at the very end of the fjord, where you can see the ocean. The fjord is 6 kilometers wide from south to north. So think of a 5K race. It's 20% longer than that. So it's a big place. This is a bird's eye view. Let's take a moment and instead look at Helheim Glacier from the ground. So we're going to stand on the fjord wall and look west towards the advancing ice front. This is data from a terrestrial LiDAR scanner. It sits and it is looking at the front of the glacier, monitoring its movement, measuring its height. So Helheim Glacier is almost 100 meters tall, 100 meters above sea level. It's similar to the Statue of Liberty, which is 93 meters from base to tip of torch. But Helheim actually has a lot more ice than that, and most of it is underwater. So what we're seeing here is just about 1/8 of the water that the glacier, 1/8 of the ice that the glacier contains, and the other 7/8 are below sea level. What else do you notice? Maybe you see the ice bumping up and down as it goes along. As the ice flows out seaward, it's rising and falling and rising and falling. These are the tides. So up and down, twice per day. And this is about 3 days worth of data. So we see the ocean lifting up millions of tons of ice and setting it back down again 6 hours later. So the power of the water. Water is really important to Helheim Glacier. You saw it in the first image. You saw the melt pools forming on the glacier. You see the ocean doing its heavy lifting here. If we zoom back out to the whole catchment scale of the entire Helheim Glacier, we'll find water there too. So here's the exact location of Helheim in southeast Greenland. And these colored dots are places where liquid water has been detected inside the ice sheet. So it's not at the surface, and it's not underneath, and it's not the ocean. It's inside the ice sheet. It's this hidden strip of water that we can't see from the surface, but we know it's there from NASA data. I want to show you what that water looks like, but to do so we have to go to Antarctica. So I guess for the very first time in Vail Symposium history. Pretty cool. Let's go to the Ra-Badouan ice shelf in Antarctica. It's named after a Belgian king. And my colleague Jan Leenerts at UC Boulder calls this the RBIS, the relatively boring ice shelf, he calls it. He went here because he wanted stable, boring conditions to take an ice core and measure the annual layers so that he could know how much snow had fallen there in the past. But as you saw, this ice core was full of water. There's so much meltwater here, it had just absolutely destroyed those pristine ice layers that he wanted to study. And instead, he found this borehole full of water. So they lowered this camera in and found this subsurface lake. 4 meters below the surface of the ice, there's all this liquid water. So I don't have amazing footage like this from Greenland, but I can tell you that it's pretty similar. All of these colored dots are individual data points where water like that has been detected. And in Greenland, it's 10 to 20 meters down. You have to go 10 to 20 meters down before you hit water, compared to only 4 meters on the relatively boring ice shelf. So it's a tougher environment. And this is why we went here this past June. We went to this exact pushpin at the end of one of these endglacial aquifers, one of these endglacial water stores, where we think the water drains into these crevasses, and we think it reaches the bed and affects ice flow from there. So we went here, and we went this past June. We chose June because climatologically speaking, it's the best time to go to the Arctic. It's near the summer solstice, so you have lots and lots of daylight. It's not super warm and melty yet. That kind of happens in July. July makes the most meltwater. And it's also warm. It's not still cold from the spring, April or May. So we chose June, and we got all of those good features. But what we didn't count on was the amount of wind that came this particular June. So some data over on the left, a map of average wind speed throughout the month of June compared to normal. So blue areas are less wind than normal, and red areas are more wind than normal. So we had substantially more wind than normal that we hadn't planned on. We were prepared for it, and we survived it, but it ate into the amount of science that we were able to do. The helicopter pilots who flew us up to our field site were really fascinated by these conditions, and particularly by the fact that we were going to live and work in them for 10 days. We had to spend the first 2 days of our field season in absolute survival mode. We cut these snow blocks and built this 5-foot-tall wind wall. We called it our wind shield in order to protect our tents from being covered in snow. And before we had built our wall 5 feet tall, actually we had to build another wall behind it. We had to do sort of double-duty wind shielding. Before we had erected that wall, we had to get up every 3 hours through the night to shovel our tents free of snow. And there was no choice, because if you don't shovel your tent out, you suffocate. So, it wasn't like dangerous. Like I said, we were prepared for it. It was just a lot of hard work, the kind of thing that you get in the Arctic when it's changing due to climate change. So we built our wall. We had 8 days of our field season left, and it was fantastic. We got to do a lot of experiments. Here we are retrieving instruments, taking data, finally relaxing and getting a meal in the cook tent. And then our prime mission was to install these GPS stations, one of which you see in the bottom right there, that are going to measure the motion of the ice and the stretching of the crevasses that we think might carry the meltwater to the bed. So here is, here is one of the GPS stations after we had finished setting it up in June. It's awesome, it's perfect, everything's sticking up in the air. We've got a solar panel to give it power. We've got an antenna that allows it to communicate with the GPS satellite constellation. The antenna is 2 meters up to allow for all the snowfall that we expect over the winter, and we also sunk it 1 meter down into the snow to stabilize it. So things are looking really good. And then in September, just 1 month ago, we went back to retrieve the data. Or rather, my awesome postdoc, Jessica Mejia, was the person who went back and got the data. We checked before we went. The GPS stations are there. They're visible from space. You can see them as tiny little specks. The box that you see next to the solar panel is about the size of an armchair. So they're visible, but they're not huge. They're there, they're working, they're communicating, and they're measuring the widening of this crevasse. It's a 15-meter wide crevasse, bigger than a tractor trailer. And when Jessica went back, she took this footage of the crevasse and a couple of new neighbor crevasses that had opened up over the summer that we didn't anticipate getting as big as they are. So the helicopter pilots really loved this too. They're adventurous people. They love to fly in this terrain. Okay, so the GPS stations were working, but they weren't perfect. They had some problems, and let me show you what those problems were. I told you how good they looked in June, and then when we came back in September, some of them were in pretty good shape. The antenna is up, pointing roughly at the sky, and some of them not so much. Some of them, apparently we had a week of very strong melt in June after we left. And so the 1 meter worth of pole that we had buried in the ground, about half a meter of snowmelt happened. So now we've got 50 centimeters of pole anchoring this thing that's going 2.5 meters in the air, and the wind is blowing 25 knots. So you can imagine why some of them aren't looking perfect anymore. But incredibly, they're all still communicating with the satellites and registering data, and Jess was able to go get that data. I'm going to share the data with you. You are the very first audience to see these data. They're hot off the presses. Okay, here we go. This is a time series, so moving forward from June all the way to the mid-September, of how much the ice is stretching. So positive numbers is stretching ice. The ice is expanding as it flows. And negative numbers, if there were any, would mean that the ice was actually compressing as it's flowing, so as if the crevasse were closing up. But that's not what we see. All the numbers are positive. The crevasse is opening up. So there's a lot of things happening here, and we think we've got the sequence of events figured out. So let me walk you through it. First of all, there's 5 days in late June during, I mentioned there was all that snow melt where the poles started to come out. That melt, we see evidence of it getting to the base of the glacier because we see this additional rapid stretching happening over the time when the melt was happening. So that water is getting to the base of the ice sheet and aiding ice flow and helping the ice stretch out as it flows towards sea level. So this is the evidence we were looking for, that this water is actually getting to the bed. There's a lot of other things going on in this plot. So the next week, the data look a little bit different. We're not really stretching the way that we expect, but we figured it out. This is when the GPS pole fell over. So this is not scientifically interesting, but it's something that we have to understand and take out of the data. So the GPS pole that fell over is one that's slightly further downstream, and the pole fell to the right, so it actually fell away from this other pole. So it's as if it enhanced the motion of the ice and enhanced the stretching compared to what was actually there. And then what happened next is the other pole fell over. And this one fell more rapidly, and this one fell towards the first pole. So as the antenna moved, it looked like the ice was actually compressing, or rather not stretching as much as it is in truth. So we don't want to look at the data in that gray box because that's when the poles were falling over. But we do think we can interpret the data that's not grayed out with some confidence. So we see relatively steady ice flow through the rest of August and September, which is about what we expect. Oh no, I've pressed a button I didn't mean to press. Okay, great. So the GPS data actually corroborates data that we saw from the helicopter as we were there. So footage from June is on the left. There's the crevasse that we placed our GPS units around, pretty small. And by September, it had substantially widened, and you saw before that some cousin crevasses had opened locally too. So just to remind you, there's this liquid aquifer water inside the glacier that is flowing into this crevasse and stretching it open and widening it, and getting all the way to the base of the glacier, where it changes ice flow. We didn't know that water could get to the bed at this particular location. We've long understood how subglacial water networks work. So this is excellent modeling work done by Aaliyah Summers, who has studied the paths that the water takes underneath the glacier. So she can actually predict the exact flow paths that the water takes. And it's a lot like a terrestrial river network. Right, there are branches that coalesce and join up, and we get these two major channels that flow out of the end of the glacier. But what we didn't know before is that the water network actually starts substantially farther upstream than we knew about before. So we're having to redraw our maps. There's more melt, and there's meltwater in places that there wasn't meltwater before. As Greenland continues to warm. And this is only going to keep changing. So just to wrap up, the conditions in Southeast Greenland are extreme. We were prepared for them, but we didn't want them. The wind and the melt ate into our field season time and changed our GPS data in a way that we have to be aware of. The climate change in the Arctic, the climate change in southeast Greenland in particular, is like nowhere else that I've seen. It's an extreme environment with extreme changes, so it just stacks and builds. I told you we have to change our maps of where the water is because there's more melt and it's happening further inland as the climate warms. The melt is moving to higher elevations. And even though it's difficult, it's so important to keep collecting data and asking and answering new questions that are questions that we have to ask as the climate continues to change up here. Thank you for your attention and interest, and I'll give the stage back to Scott.
Thank you, Kristen. So our next speaker is Ted Scambos. Ted is a senior researcher, research scientist at the University of Colorado in their Earth Science Observation Center, which is part of CERES at the University of Colorado Boulder, which is one of the climate institutes that are paired with some of the national labs in that same area. So prior to his current position, he was the lead scientist at the National Snow and Ice Data Center for about 14 years, which is also part of the university. He received degrees in geology, geochemistry from Stony Brook University, Virginia Tech, and the University of Colorado. Ted's research has focused on the use of remote sensing to study the great ice sheets and polar sea ice and investigate the effects of climate change on the poles. He has been on 21 expeditions to Antarctica, working with British, Australian, South Korean, Argentinian, and Norwegian research programs to explore most of the areas of the continent and its surrounding ocean. Ted has published extensively on polar ice loss and glacier acceleration changes in Arctic and Antarctic sea ice, the evolution of icebergs, wind-snow interactions on the high east Antarctic plateau, and using satellite data to find the coldest place on Earth, which he hopes to visit and install automated climate instruments. He is the principal investigator for the Science Coordination Office of the International Thwaites Glacier Collaboration and a member of the Landsat science team. Welcome, Ted.
Thanks a lot, Scott. Get my water here. Well, thanks. Hi, everybody. Yeah, nothing like Antarctic conditions, but it certainly was an awakening after a nice summer. And being stuck at Vail Pass, pretty much at the top of Vail Pass while the weather got worse. We were actually checking how much food we had with us inside the truck in case, we had to spend a few days there or something. Well, this actually is the outlet area of Thwaites Glacier, which is the widest glacier on Earth. Now, nothing from Kristen. Helheim Glacier is a huge glacier, but by that standard, Thwaites is truly gigantic. It's about 120 kilometers wide, about 70 miles wide, and it extends into the Antarctic ice sheet, covering an area similar to either the state of Florida, but I kind of prefer, it's a little bit bigger than the state of Georgia, and it's sort of shaped like that, where there's a very wide outlet to the ocean, and then a big patch of land that's draining through that area into the center of the West Antarctic ice sheet. West Antarctic ice sheet, it's in the Western Hemisphere. East Antarctic ice sheet, Eastern Hemisphere. So how are climate change in Antarctica, how is climate change and Antarctica connected? And this is sort of a big picture view, and it is simplified. I have to kind of wrestle with my fellow scientists to get them to accept that this is a reasonable presentation, but it's a good one for our audience here. Basically, these large blue arrows are showing that there's an increasing wind field around the entire continent. Now, this has always been there. It's always been a westerly wind blowing around the Antarctic. But it's gotten stronger in the last several decades. As warming in the tropical areas increases, you're sort of pressing the big circulation patterns like trade winds, and the reason that storms go from the northwest generally to the east, southeast in the United States, all of those big patterns in the temperate latitudes are squeezing the air around Antarctica because that ice sheet sticks up so far into the atmosphere that it actually affects the airflow. And so you don't push many storms across Antarctica, they've got to go around. Well, when you warm up the higher latitudes, you sort of squeeze those winds a little bit tighter around Antarctica. Now what that does is it moves the ocean differently on the surface. So by moving the ocean surface differently, you tend to push things both to the east and outward away from the continent. And what that means is that water that's deep down in the ocean comes up to fill in the water that's being pushed away from the continent by these stronger winds. That's a problem, and it's a problem that's a problem right in this area especially, an area sometimes called Pine Island Bay. I think scientists are kind of calling it the Amundsen Sea embayment now because the name of the patch of ocean right there is the Amundsen Sea. So what you see in this area is melting at depth. Warmer ocean water is being drawn in to the coast of Antarctica and melting the underside of very thick flowing ice that's trying to get out to the ocean. This process was there a little bit in the past, but because the winds are getting stronger, it's happening more and more, and we're seeing this area of Antarctica lose ice quite a bit. Another area of interest that we can talk about if we get to it will be a place where there's a lot of surface melting, and the processes that Kristen is talking about are in play in this very northern tip of the Antarctic Peninsula, which is the part closest to South America. Here's a kind of a cross-section view. Now, there's a lot of complexity on this cross-section, but basically what I was talking about is that the winds are pushing the surface water away. It's allowing something that we call circumpolar deep water, which is actually quite warm, a few degrees above freezing, enough to melt lots of ice in a given year. It's being drawn up onto the continental shelf around Antarctica, and it gets right to this point where the ice is going afloat. This is a schematic of Thwaites Glacier, and this area is getting eroded quite rapidly. That's causing the glacier to flow out more rapidly. There's a lot of other features on there. This is part of a proposal that led to a big international effort to study Thwaites Glacier, and this diagram was supposed to put everything for everybody in one place. This is a map of how the surface of Antarctica is changing, and we used two really detailed satellites, really accurate measurements of surface elevation, separated by about 20 years. They're laser satellites, so similar to that colored profile that Kristen showed, which I think was acquired from the rock outcrops right next to Helheim. This is a satellite in space that measured the elevation of Antarctica very sensitively twice, more than twice, but two patches of data separated by about, I think it was 17 years in total. And all these red areas are areas that are losing elevation because the ice is flowing out faster than the snowfall is replacing it. And that right there is Thwaites Glacier. There are a few other red areas around the continent, but you can see that this is really the place of greatest concern, where we're seeing rapid flow, faster flow, and elevation loss because the ice is not being replaced by the snowfall above it. So I want to give you another window into why Thwaites Glacier in particular is probably the most important glacier on Earth for sea level rise in the future. This area of West Antarctica, you're sort of seeing a kind of a satellite or an astronaut's eye view. And, whoops. Yeah, so this whole big dome here, huge. Here's Thwaites. It reaches into the center like this. I've got to stop using that laser, I guess. And so there's Thwaites, the bedrock of Thwaites, and you can see that there are some really deep canyons if you move away from the coast and into the center. And that's a key part of why this glacier is not very stable. it's kind of riding up on this higher ground near the point where it goes into the ocean right now. So it's slowed considerably as it flows up over this ridge. It's below sea level, but the ice still has to thin to get over it. If you lose contact with this area right in front, and remember I said warm ocean water is coming in here and melting that area right now, you start to have it step backwards into this deep basin. That's going to allow the glacier ice, and again, it's state size. It's the size, it's bigger than Georgia, but it's sort of shaped like Georgia, to flow out a lot faster. So if you can think of Georgia ice cube a mile thick being dumped into the ocean, you can imagine that sea level rise is going to take a significant increase. And if we're just talking about Thwaites Glacier, darn it, well, whatever. If we're just talking about Thwaites Glacier, we're talking about 2 feet of sea level rise. Now, it's going to take several centuries for something like that to happen, even with a very fast unloading of the ice. But the problem is that in those 2 centuries, you're also going to begin to incorporate some of these other large glaciers. The drawing down by Thwaites will pull the ice in from these adjacent areas. So you'll see about 6 feet, 8 feet of sea level rise coming from this entire area if we really go to the end game. The problem is not really 2 feet or 6 feet or 8 feet of sea level rise at the end of a millennium of ice loss in Antarctica. The problem is that within a century, possibly within several decades, the rate of sea level rise, all of our coastlines in the US, Europe, China, everywhere, will start to go up faster than we're used to. We'll start to go up fast enough that we have to build and spend a tremendous amount of money on infrastructure to protect New York City, Miami, San Francisco, Shanghai, London. All of these places are looking at the long-term cost of protecting their waterfront because of sea level rise. And the wild card in all of that is this area here, starting with Thwaites Glacier. And that's what Thwaites looks like in about a 6-8 year movie made from satellite pictures. And you can see that it's sort of falling apart. This area is flowing quite a bit faster. This area was safe enough to work on, and I'll show you some pictures from our field camp there. But you can see these cracks. It's starting to fall apart. This area up here is flowing faster again. We think this area here is actually going to be kind of relatively stable. It's not immediately going to accelerate, but the acceleration is going to go into the ice sheet this way and also up this way towards this deeper, thicker area. Sorry about that. There's our camp. We were there in 2019 to 2020, December to January, so it's the warmest time of the year in Antarctica. Just like Kristen, we want to be there. In the summer months, we got lots of daylight. That's a safety feature for both temperature and just for working in the area. And then we've got quite a bit of equipment at this camp. We're actually going to drill through about 1,000 feet of ice and put instruments. We're actually floating on the ocean here, but it's pretty safe because it's about 1,000 feet of ice before you get to the ocean. So you sort of bunk in these tents here. This is where you sleep every night. 1 or 2 people in each of these tents, depends on how many tents we brought, and then a tent for science work mostly, and a tent for food, cooking, and also meetings. So that's what it looks like inside. It's crowded. It's, we got science and food and fun and stuff happening at the same time, people talking. This woman here, this woman was our mountaineer expert. She's a heli ski guide at Revelstoke. And this guy was a computer programmer that worked with me, helped make the instruments work with microcode that connected all of the sensors together and had it transmit over Iridium to our office. I keep pointing at the screen. And then a couple of friends, my PhD student there, the woman, and then that fellow there sitting on the right was a writer for a magazine article. He wrote actually several articles about this trip. And not to be outdone by Kristen, I hope we have. Can you see if you could make that video go forward from there? Yeah, there you go. I think you just need to click on that little arrow there. in the lower left. Nope. Yeah. Okay. Well, needless to say, it's windy and loud. In fact, so loud you can't sleep some nights because it's, there we go, but we need the sound on. Yeah. So it's like this, about once every week or so, where it's windy enough and you get, it's warm enough where that blowing snow, it's below freezing, but it hits your clothes or your face and it melts. And so if you're outside trying to work, your clothes get wet, and then it really does get dangerous. You get into this losing game with, you can't keep yourself thawed and warm well enough over time. So yeah, I wanted to talk about sea level rise. This is from the last IPCC report. And there's several estimates of where sea level rise is going to go if we just consider all of the other possible sources of sea level rise besides the ice sheets. And that dashed line there that's flying above all the others has to do with whether or not Greenland really unloads a tremendous amount of ice, or more importantly, whether or not West Antarctica becomes unstable and begins to radically increase how much ice is flowing off of the continent. Sea level rise has been fast in the past. This is a record of sea level rise over the past 20,000 years. And there have been periods of time where you see these very steep increases. The Earth had several big ice sheets on it. The Laurentide, the Scandinavian ice cap, Greenland was bigger. Parts of Antarctica were also lost. But it's possible that you can see 2 and 3 meters of sea level rise in a single century when you got these big ice sheets collapsing. Now we're at a point where it's been extremely stable. All of civilization, the invention of agriculture is somewhere in here. And then, cities, city of Ur, Egypt, everything happened in this extremely stable period for sea level rise and for climate in general. We have been living through the golden years of the past 800,000 years. And now we've begun to change that in a big way. So we're going to change the game a little bit, talk about Antarctic sea ice, which Scott brought up. This also is a movie, and I'm not sure I'm going to be able to play it from here. There we go. And it's just showing you how that floating fringe of ice sort of ebbs and flows around the continent. It's one of the biggest changes on the surface of the Earth is when the Antarctic Ocean begins to freeze over. Now, this was several years ago, 2011. It just cycles through the 2011 annual cycle over and over again. But what we've seen this year, as Scott pointed out, is it's just wandered off into a pattern all by itself. This is 45 years of satellite data covering how the Antarctic ice sheet grows and shrinks every year. And this year, pretty clearly, stands out all by itself. Why is this happening? I'll try to pick it up a little bit. Well, first of all, take a look at what that means in area terms. It's not astonishing how much less ice there is, but it's significant. You can see right away that there are big patches of the ocean that are almost always covered by ice at this September, October time of year, but big areas of the of the ocean are not covered. Why is this happening? It looks like there's this close correlation between another graph that Scott showed you, record warm ocean temperatures, and some of these patches where the ocean is exceptionally warm this year seem to be close to the areas where this sea ice growth has lagged behind quite a bit. So what we're thinking is that somehow this warmer near-surface water has gotten in close to the Antarctic surface water. Now the reason that's probably a little exceptional is that ordinarily, all of that ice that I showed you, the big fringe around Antarctica, is sitting in slightly colder and slightly fresher water, sort of like a big dinner plate of water that's really close to the freezing point, and the sort of sea ice comes and goes every year. And other water types in the ocean don't mix into it very often. It stays sort of isolated from the rest of the ocean. That apparently isn't happening anymore because these warm patches here are somehow turning southward, and we think we know why. Has to do with bathymetry in these areas and mixing into the surface water and inhibiting the growth of sea ice in the winter maximum period. And so the loss of sea ice makes the coast more vulnerable. Wave action starts hitting all these glaciers. All these purple streaks are fast-flowing glaciers coming into the ocean, and that makes the edge of the ice sheet more unstable. If it begins to flow faster, then you increase sea level rise. And it's a major driver for the ocean. Formation of sea ice creates cold, dense water that then sinks into the bottom of the ocean. And because it does that relentlessly, hundreds of years, thousands of years, you sort of stir the entire ocean, mostly from the bottom, and then all these upwelling areas. It's a major driver for the vertical circulation of the ocean. The other major driver has to do with the northern North Atlantic. But Antarctica is a big part of this. And it's slowing down because of warmer conditions and less sea ice. So what about low temperatures? And we can talk more about this afterwards, so this is going to be a bit of a diversion in a way. We use satellite data to map the coldest temperature on Earth, and that's, of course, in Antarctica. It's in central Antarctica. Now, the record at any base is about 130 degrees below zero. But we went looking at places that hadn't been occupied by a weather station or a base and found that there were places that appear to get down to about 140 to 145 degrees below zero. And this is a map of the area. All of these colored areas reach extremely low temperatures. This is where the past air temperature record from a weather station where a guy went out, believe it or not, in 130 degrees below zero and dusted off the instrument and read it, was 130 below. But we looked uphill, these green lines are the contours for the ice sheet, and found a whole bunch of places along in here that get extremely cold. So we're interested in whether or not this is happening more or less often going forward, because greenhouse gases in the atmosphere should inhibit the ability of the surface to reach these record cold temperatures over time. We have about a 20-25 year record of surface temperatures in this cold wintertime conditions. So, of course, we're interested in going out there. Well, those are just some of the events. It's just showing that multiple satellites for the same event reach these low temperatures. In other words, it's a confidence measure that we really are seeing this. And we're interested in going there with instruments to stay there through the winter. We would go in the summer. It would be about minus 35, and then let the instrument stay there and tell us how bad it got in the middle of winter. Well, thanks. Kristen and Scott and I will all take your questions. Well, I think we've got some discussion going before that.
Great. Thank you. All right, so we're going to spend about 20 to 30 minutes talking about some of the research that both Kristen and Ted have done in the ice sheets and glaciers, and then we're going to open it up to questions from the audience. So I'm an electrical engineer. I'm not a glaciologist, and so coming up with questions was a challenge for me, but you'll have to bear with me. I guess the first one I wanted to start with Kristen is to understand a little bit more about, so what's the impact that groundwater has on the stability and the flow of a glacier? So it sounds like these big crevasses have allowed groundwater to go to the basic bedrock of what holds these glaciers in place. So tell us a little bit more about that.
Yeah, I think the simplest answer is it's complicated. Of course. Most of the time when you have a big crevasse that's bringing meltwater to the base of the glacier, the default assumption is that meltwater lubricates the base of the ice and the glacier can flow faster. But it's not always the case. Sometimes you add more water to the base of the glacier and it will actually make the glacier slow down. And this is surprising, but I'd like to explain it through, and then we can see maybe that it makes sense. There's this network of channels at the base of the glacier. The water organizes itself into this network of rivers, which I think I showed. And these channels, they they eat into the ice. So there's all this water on the base of the glacier, and the water is flowing downhill, and it carves up this channel by thermal erosion. Just the speed of the water and the friction carves these channels that are like a meter or two, like rainbow sized. So here inside the channel, there's ever so slightly less ice on top of your head than there is over here. So the pressure is higher here, and this makes water scoot into the channel. So this low pressure environment actually sucks water into itself. Now you have more water, you have a higher water flux that's flowing, and now you can erode a bigger channel. And so they grow through this virtuous feedback. They just get bigger and bigger and bigger. And as they get bigger and bigger, they suck water away from larger and larger regions. And that dries out the bed over here and increases friction. And so this is how you've added more water. You've increased the friction in most areas of the bed. Of course, you've greatly reduced friction right here in the channel, but most places are dried out, and now the glacier is going to flow more slowly.
It's not every evening you get to understand the Greenland ice sheet through interpretive dance. Here at the Vail Symposium, we break those educational boundaries.
I can't wait to see what you're going to dance
Oh, God,
for.
no.
So yeah, it varies place to place, and it varies by time of year, and you don't know until you go to measure it. Well, I guess you can have a reasonably good prediction, but there's a lot of variability.
So it's complicated.
It's complicated.
So Ted, you've been to the Antarctica 21 times.
Yeah.
So tell me some experiences, tell me some stories about what you've seen and what is just, that's an amazing amount of time.
Gosh. Yeah, I've been to all of the areas in Antarctica, the interior, the coast. I've been on ships looking at the sea ice. Experiences, gosh. Before GPS, it was much easier to get lost. We used to use bamboo poles quite a bit. And one time we were driving up this hill. We knew it was a hill. It's extremely flat and shallow, but we knew we were driving uphill very gradually. And me and this partner, Nadine Narrison, she was at University of Washington, where you got a degree. Anyway, we're driving up, and we actually didn't look behind us. We were doing our GPS stuff, and then we kind of 2 minutes at one pole and then drive further. Turned around, and this fog bank had come up and completely obscured all of the poles that we couldn't see between one and the other. They were about 500 meters, but about 1,500 feet apart. And what we had to do was cling to the one pole we were at and talk about it, and then one of us would drive out until they were sure they could see the next pole, because the wind was blowing and it was kind of covering up our tracks a bit too. And then she was in front at first, raised her arm, and then I would have the guts to leave the pole that I was at and follow her to the next pole. And then it got to the point where she was starting to disappear before she could see the other pole, so I had to leave and keep an eye behind me, on the pole behind me, as we were driving down. We had about 20 miles to go in that mode. That was that wasn't any fun. Cold stuff. We were in this one place where we were studying this large dune fields, and for some reason NSF wanted us out there in November, which is spring, early spring, and they're dune fields. It's a very windy environment. There's only a month or so where it's not windy, and that's January, which we told them. Anyway, it's extremely cold, minus 35, and the wind is blowing, and we're trying to set up our tents, and I'm realizing that I can't keep both eyes open at once because they're trying to freeze shut. So I'll take my finger and wipe the ice off of my eyelashes with one eye and work with that eye for a while until it starts to get really heavy. I'll wipe the other eye and work with that one for a while. Yeah, that was brutal. Okay, it's It is mostly hard work. There is a lot of frustration. I think a little bit less in Greenland. Weather is your enemy in Greenland. NSF and the logistics are also a big challenge in Antarctica because it's a very big operation and there's a lot of moving parts. The Air National Guard and their aircraft have to be working. Fuel has to be in the right place. McMurdo has to be ready with your cargo and ready to get you moving out of there. That's the big base, McMurdo, that the U.S. has. And then you get out there. And very often your season is constricted either by weather or by logistics. And so you've spent months getting ready. And in the end, you have to try to do, 2 or 3 weeks worth of work in the space of a week or 10 days or so. That's a lot what it's like. But I've been 21 times. I really enjoy it. I enjoy the challenge. The people that I work with enjoy the challenge. Most of the folks that go to Antarctica, they want to go again. They want the logistics to go a little bit better. They want to be lucky with weather, but that's weather. But they do really want to go again because it's such a spectacular environment.
You're going to have to explain the doomsday concept of why they named it the Doomsday Glacier.
Yeah. So Thwaites, as I told you, has this potential for really accelerating the rate of sea level rise. If it begins to really step back from the coast and get into these deeper areas where it's very thick ice and it will squeeze out much faster. We had a reporter with us on the first trip that we did under this current project. It wasn't the first time people had been to Thwaites, but only a handful had been there before. So this is like first time 40 people in front of Thwaites and another 50 or 60 on the surface in various camps, all working at the same time. Wasn't Andy Revkin, it was Jeff Burdell, Jeff. He's on Goodell, that's it, yeah. Wrote for Rolling Stone, and the title of his the title of his story was The Doomsday Glacier, just The Doomsday Glacier. Because he had been filled up, he'd heard so many stories about how this thing is going to come apart and flow faster and raise sea levels at a pace that is going to be very uncomfortable for us to manage in the coming end of this century and in the next century. It will be very hard not to have that happen, but we do still have a window of time where we can slow this process down, possibly stop it, but more importantly, slow it down to something that takes thousands of years to unfold rather than a century or so. Sound doomsday enough for you?
Yes. What I see is doomsday is the off-the-chart records that we're seeing. And I understand we're entering an El Nino season, so we expect temperatures to go up during that period. But they're going up so much faster than we've seen historically. And both of you have extensive experience in polar research. Do you think we've hit a tipping point? And is it do you feel like it's irreversible at this point?
It's hard to know because the climate system, well, glaciers in particular, operate on really long time scales. And they have a lot of year-to-year variability, as I think we've both been talking about. So, yeah, if something has tipped, like the Doomsday Glacier, like Thwaites Glacier, Thwaites Glacier is going to take a minimum of 400 or 500 years to unleash its full fury. And none of us will be alive, and none of us will be, taking observations. And it's really hard to see when you're just on the first, 10 or 20 years maybe of something that's tipped. It's really hard to identify it.
Yeah. And by tipping point, the idea is that the system reaches a state where it's about to change and no further pushing is necessary to get it to change the rest of the way. So for Thwaites, that means it gets thinner and the place where it goes afloat steps back a little bit. And then even if you stop pushing more warm water through what we do, the atmosphere, up against it, it will eventually collapse. but there's still a big question about how fast that happens. And there are lots of tipping points in the climate system. Some of them have probably tipped, and some of them, we still have a chance to turn things around. The things that are the most dramatic, like ocean temperatures, Arctic sea ice, in theory, or in imagination, maybe I should say, they can be turned around fairly rapidly if we were to reduce CO2 in the atmosphere. But the things that, like the warmth that's being trapped in the ocean or the evolution of the ice sheets, it's hard to know if we have tipped, and it's hard to turn it around if it's already begun.
So there was I can't remember what study it was, but they're basically saying that at 1,000 gigatons of CO2 that we add to the atmosphere will impact the amount of heat that hits the Earth and is retained and cause significant sea level rise. Now, we've done about 500 gigatons already, and we do 50 gigatons every year. And so we can see our way, in my lifetime, to that number. Tell me, how do we keep that from happening? Because that level rise is devastating.
Yeah.
Is that 10 years, if I did that mental math correctly?
That's right.
That's
Yeah.
the scariest.
Yeah.
That's like the scariest thing I've heard.
Because I don't think it's
lately.
going to stop in 10 years. The U.S. has stopped. We're backing off on how much we're contributing, but China and India are still accelerating quite rapidly. They get it about climate change, at least would appear they do, but they're quite interested in having their economy develop first before they commit to decarbonizing. I don't have a fun answer. I mean, there isn't one. You're right, Scott, you said it before. We know what it is we need to do. The technology is not outside our reach. And the thing I like to say when people say it's all bad news, because the attention of entrepreneurs and businesses has been turned in a big way towards solving this problem, that's probably a big cause for optimism, that we have a lot of minds working on this, not just from the, I want to understand this problem better and measure this area better, but I can make money because people need this solution that I'm trying to come up with. That's powerful because there's a million people like that, and that becomes transformational.
In some ways, I might say that the golden age of being a climate scientist or the golden age of being a glaciologist is already over. And the people who are leading the charge now are entrepreneurs, business people, and politicians. They're the people who are going to solve the climate crisis. And scientists who were working in the 90s and maybe the 2000s were instrumental in, demonstrating that the climate crisis is a crisis. That was really important. And, people who are still working now, I mean, it's just gravy now. We can learn more and more about the climate system, but we already know that it's a problem and it needs solving.
Yeah, the case is made, and the frontline work, the way you put it, politicians, entrepreneurs, scientists, society, other parts of society, there's more work to do understanding how fast it's going to be, maybe exactly where or which area is going to be a threat next. But yeah, I agree. We don't really have to, some people are not convinced, but we don't really have to keep making the case from scratch anymore. It's done and we know what we need to do.
So how many of you are coming for the energy lecture, which is? Tuesday. Okay. I got this from the New York Times today, and the title of this is "Fossil Fuels Aren't Going Anywhere." And ExxonMobil signed a contract to buy Poinar Natural Resources, which is a fracking company worth $60 billion.
It's in the Permian Basin.
So you have the fossil fuel industry doing everything they can to continue to invest in exploration of the one thing that is killing this planet. And so I know we have a fossil fuel person at this meeting, but I would love to have somebody ask them where their investments are and what they see the implications of those investments. But at this time, it's my pleasure to actually turn the questions over to you guys. In the back.
Oh,
I'm sorry.
one sec. I'll bring you the mic.
Yeah.
Thank you, Scott. And I know you have more, so just in case. Okay, so a couple quick things. I'll bring the mic around, and I'll ask you to just speak into the microphone and not near the microphone, because that's what it sounds like. And so for our folks online, speak into the microphone. Please stand if you're able. And I'm actually going to start with a question we received online that's a little bit lighter, maybe. For those of us traveling to Antarctica, what should we look for? And then I'll come back there.
Have you been to Antarctica?
I have, but only once.
Yeah.
Yeah.
I mean, it's mostly about the coast. For tourists, for tourism, the exciting, the beautiful areas are a dramatic landscape near the coast, the wildlife. It's incredible how rich the ocean is around Antarctica. Most of the travelers to the Antarctic go to the Antarctic Peninsula, which looks like a continent trying to fight its way up through a blanket of ice. And you really get a sense of ice glacier flow off of these high areas. You'll see whales, you'll see penguins, you'll see seals. You may jump in the ocean, in the polar ocean, at least the cruise I was on. They offered that. I did not need to jump in to know just how painful that can be. But yeah, it's fantastic, and people really like it. It's you're in for a treat.
I would say look for meltwater. There's some there, more every year, but this is why I study Greenland. I think meltwater is exciting, and Antarctica is just starting. But you'll see meltwater if you look.
Yeah, and the peninsula especially. Yeah, that's something that's kind of general about glaciology and polar science. The real transition, especially on the surface, is if you go from just a couple of degrees below freezing to just a couple of degrees above freezing. If it was minus 10 or minus 20 and you go to minus 15, you can't even tell. The surface looks the same, snow blows around the same way. But if you go from 2 or 3 degrees below freezing to 2 or 3 degrees above freezing, everything changes, and you get aquifers soaking wet snow below the surface and water seeping down to the glacier and lifting it off and riding it out to the ocean. And yeah, icebergs calving. I have more slides on that, but yeah. Look for water, because that's the killer substance in the poles.
How does the increasing population affect all of this? And what can be done about it?
It's not even just the increase in population, but the increase in population that wants an advanced lifestyle. It's energy. And yeah, I mean, thanks. I don't know what to do about that. I mean, as countries become more developed, almost every case, the population rate of growth drops. But that's all we got, is that we need to get medical care and an awareness that you don't need so many children to support you in your old age, because they're going to all make it to middle age and old age. Yeah, I don't know. To the extent the population growth is happening, they need more energy. To the extent we need more energy, right now we're going to use mostly fossil fuels. And unfortunately, it's going to be hard to turn that around fast, but we know how.
Yeah, for me, it's very much an energy problem. And the developing nations that are now trying to grow their economies need a lot more energy. And so we've got to help them with the right infrastructure so that that's sustainable for future generations.
For those of us who are interested in learning more about the topic about glaciers and the two poles, what are the sources you would refer us to?
Well, NSIDC has a great website with a lot of educational material on it. There are some books. I mean, so you would, there's a couple that I recommend to my students, and even though it's a book by National Geographic, it's a phenomenal introduction to every aspect, including the history of Antarctica, called Antarctica by National Geographic. I can try to find that on the web for you if you like. But the websites, NSIDC's, who else? Polar View.
Climate.nasa.gov.
Yeah.
It's a good one. It's
That's right.
all things climate, not just ice. But yeah, the National Snow and Ice Data Center is really a one-stop shop.
Yeah. You can go right from reading the middle school level description of what's going on to data that might, if you were interested, and would take a while to work with it, let you investigate for yourself what is going on with temperature, with sea ice extent, glacier flow speed globally. Remote sensing, he may ask this question, so I'll stop.
No,
Remote sensing has transformed polar science. The satellite stuff that started happening late 80s into the 90s, it was a complete game changer in terms of how we're able to work, what we're able to see, how we understand the system. Leaps and bounds.
Another site you might go to is called climate.gov.
Yeah.
That's an easy one to remember. So climate.gov, and it's a NOAA site, but it also takes a much more holistic picture of the climate change. And then you can actually go into their dashboard where you can look at sea level rise, ice sheets, carbon dioxide, ocean health. It has all the major areas covered in it, so that's a good resource.
So first of all, thank you all for your expertise and your time and weathering to get here. Just a comment that I would have, and you brought it up, Scott. Next week we're doing this program on energy, and these are complex issues, obviously, and so we're talking about your expertise tonight, but Scott, you're the entrepreneur, and I think this question is really for you, and it's off topic for tonight, but you brought it up and you mentioned it. You asked the question. It's economy, right? We want to have more children because it feeds the economy. Mm-hmm. And so we're driven, we keep talking about demographics, and we can all change our light bulbs and do things like that. Those are minor things when we talk about who's really causing this problem, right? It's the big companies. And, so it's great that we all do that, but how we get to that, I'm not sure that there's a question here, and I'm not sure there's an answer, but I hope that you all will come next week for that program, because I think it'll be fascinating.
Well, if the weather's like this.
It'll be 70 and warm.
Oh, good.
Well, yeah, I don't know if there's a question, but, as a business, at the end of Ready Talk, we were, challenged. We had never started that company to sell it. We had always wanted to build a great company, but it got to a point where we got into a business that became bigger than a small company could survive in, and we started to grow slower, and that's the death of a company. And whether you like it or not, growth is super important to businesses and to a lot of the things that we do. And with unmitigated growth, you're going to have consumption of resources, and if you're using those resources in a way that's damaging the ecosystem, then that growth is very harmful. If we can figure out how to grow and not harm the environment, I think that's the path we want to go down.
Hi, thank you so much. First of all, I don't know if you knew Connie Steffen by chance. Yeah, he was probably my favorite professor, and I did some independent study with him.
I'm going to have to put my glasses on and see who you are.
Question I have, though, is, we've got these different things that can happen, like with volcanoes going off and then throwing debris into the atmosphere, which could have a negative feedback to what's happening. To where with humanity, I've heard of people throwing, talk about going with some crazy ideas, throwing reflective things into the atmosphere to reverse the amount of energy coming into the atmosphere or onto the planet. If you can talk about those two things. What the heck?
I think, well, I fear and I think that geoengineering is going to be one of the things that we do. So rather than solving climate change the old-fashioned way, reducing CO2 emissions, maybe even actively taking CO2 out of the atmosphere, it sure looks like we are going to be stuck with really poor options of, putting, reflective things into the atmosphere, or, aerosols into the stratosphere to reflect away sunlight, or, God forbid we build a space sunshade to actually reflect away a fraction of the sun's light. There's some glacier geoengineering ideas where we would build an underwater speed bump, and speed bump trivializes it because the scale of material that we would need.
I'm going to steal that.
Speed bump. It's a giant Jersey barrier to hold back ice flow. It would be the single largest construction project ever taken on by mankind. It makes the Great Pyramid at Giza look like,
Build 1,000 of those, yeah.
Is it 1,000? Yeah.
In 10 years or something.
These things aren't going to work, but I don't know. I'm not in this sphere. I just have the general foreboding that we are going to try them.
Yeah, it's hard enough to model climate, when it's natural, and if we start throwing these wild cards into it and driving it in different directions, it'll be much tougher to make sure that we don't have unintended consequences. There's other issues also, more than just not exactly knowing what we're doing. Two things. As soon as we start, as soon as governments agree, we're going to try to do this, let's say put reflective material or sulfate aerosols into the atmosphere, it gives the oil companies latitude to keep going. And even though there could be all kinds of political statements or treaties or whatever that say, okay, we're not going to go down this road, we're going to continue to try to walk away from fossil fuels, the pressure will be too great. We got this thing keeping the earth a little bit cooler than it would be. We're not ready to give up on fossil fuels because it's dollars, billions of dollars just flow out of the ground. It's just too easy. That's one risk. The other risk for doing anything other than trying to back off the CO2 in the atmosphere, either how much we're putting in or actively removing it, like Kristen mentioned, is liability. If you've put aerosols into the atmosphere and a country can make the case that you ruined their agriculture because of an unintended consequence from that geoengineering attempt, they're going to be really pissed off and they're going to want a lot of compensation, or if there's a storm as a result. The other point about the speed bump idea is we would spend tens of billions to even attempt it, and we'd have to build the ships first that could even do it, and then we've solved the problem for one corner of Antarctica. It's being talked about for Antarctica. And so other places would reach these emergency states. And rather than spend that $50 or $60 billion on solving the underlying problem, we will have spent it on a speed bump that probably won't last all that long, and we have to turn around and build another one fairly soon thereafter. It's just not a good road to go down. There are a couple of things that look interesting in terms of pumping water out from under a glacier that look like they might stabilize a glacier, but in general, geoengineering, I haven't heard an idea yet that sounds plausible relative to spending that money on addressing the problem directly.
I'm going to take a stab at this one as well. We're doing geoengineering now. We're burning fossil fuel, and we're putting carbon and methane into the atmosphere, which heats the planet. But the other thing that we're doing with burning fossil fuel is we're actually adding a ton of particulates, so a ton of sulfur and other things into the atmosphere. That actually does cool it down because it reflects a lot of that energy. And so one of the things that happened a couple of years ago is they regulated shipping traffic and reduced the amount of sulfur that was emitted by ships. And so some of the theories on the off-the-chart numbers we're seeing is because of that. policy change. The U.S. government under Biden has, I think it was last year, agreed on like a 4 or 5 year, $500 million research study on sulfites and understanding, can we aerosolize these into the atmosphere and cool down the planet? And it's exactly that. It's trying to give fossil fuel companies a little bit more runway to keep burning their products, and that doesn't work. And one other one that I'm going to point out, which drives me nuts, is we're spending a lot of money on ideas on how to capture carbon out of the atmosphere and store it in the ground. And the Department of Energy has a moonshot. A moonshot is basically a go out and see if you can get this done kind of goal for carbon capture and storage. In 10 years, they want to get it down to $100 per metric ton. And so let me put that in terms that financially you can understand. So today we don't charge for polluting the atmosphere with carbon. If we were to reduce 1 part per million of carbon in our atmosphere, and each year we're adding between 2 and 2.5 parts per million, we're above 420 right now, it would weigh 8 billion metric tons. And at $100 per metric ton, that's $800 billion for 1 part per million. So the idea that we're going to continue to burn fossil fuel and then later we're going to suck this out of the air and store it somewhere in the ground is ridiculous. And so the geoengineering is happening today because we're burning fossil fuel. We're changing the climate because of that. And I don't think there's an option not to do it. I think we are on a path that is going to force us to come up with these crazy ideas on dimming the sun. And that to me is absolutely insane. Okay, I've said my piece on that.
It's insane,
Sounds
but we
like
have
we
to
agree.
do it. You're saying we have to be insane. Is that what you're...
We're insane right now.
Okay, I accept that.
Scott, you don't happen to have an optimistic closing question for our panelists, do you?
Well, it's interesting. So I ask students when I give them a lecture, and I'll talk about the climate, I'll talk about the numbers, and then I'll ask them, do you know what a heat pump is? And so, 2 weeks ago, I lectured to 5 different classes. 3 were entrepreneur and 2 were finance. And so they're all in the business school. And 0, and these classes had 40 to 50 people in it, 0 knew what a heat pump was. And so if we don't understand the solutions to climate change, we are never going to solve this problem. And so in my mind, we have a crisis in education. We have a crisis because we don't understand the things that are happening to our Earth systems by continuing to live the way we're living, and we have to educate that student population with information on what's going on and what are the solutions that we can do to solve this problem. So I am optimistic from that perspective because I think that next generation is gonna, and I think entrepreneurship, businesses get it now. They understand the implications.
Please join me in thanking Dr. Ted Scambos, Dr. Kristen Poinar, and Scott King.